There is a Buddhist phrase that goes, 苦海无边,回头是岸. It means, the sea of bitterness is boundless, turning back is the shore. Almost 40 years ago in 1985, the folks at Intel found themselves on their own sea of bitterness. Millions of dollars in losses, horrible manufacturing yields, an entire product category under siege. And then somehow they turned back and found the shore. In this video, we look back at how Intel once saved itself. Before we move on, just a reminder about the Asianometry Patreon. Early access members get to see new videos first with selected references. Early access really helps a lot, and I appreciate every pledge. Thank you, and on with the show. Intel's founding goal was to produce a standardized, low-cost MOS memory chip for big computing systems. Such systems then use core memories to store the data they had to have at hand for computations. These core memories were made from tiny rings of iron-based ceramic, which can be magnetized to store a bit of data, 1 or 0. Core memory, which you might recognize from my video about An Wang and Wang Labs, was superior to drum memory, but it was also still bulky, power-hungry, and slow to read or write data. Then in 1968, Robert Dennard patented the concept of dynamic RAM, a small, simple MOS capacitor carrying an electrical charge representing a bit of data, plus a single access transistor to manage the charge going in and out. One transistor, one capacitor. That is it. The idea promised a small, power-sipping alternative to core memories, but someone first had to go and make it. In 1969, after a year of agony and experimentation, Intel introduced the Intel 1101, a 256-bit MOS static random access memory, or SRAM. Drawn up entirely by hand and made with Intel's newly developed silicon gate technology, the 1101 was the first high-volume MOS semiconductor memory. It worked fine, but with 6 transistors it cost too much, 3 cents per bit. To compete with core memories, they needed fewer transistors. For their next chip, the 1102, Intel collaborated with Honeywell. The 1102 was supposed to be a 1 kilobit DRAM with a 3-transistor memory cell, but progress bogged down due to technical issues. They eventually got it working, but by then, the product had already been eclipsed. Another Intel team had been working on another DRAM memory in parallel with the 1102, the 1103. The 1103's memory cells also had 3 transistors, but design lead Joel Karp, working in conjunction with the brilliant Barbara Manes, simplified its structure using what is called a buried contact. A buried contact is a point of electrical connection, but buried, quote-unquote, inside the silicon. This let Intel directly connect the capacitor's gate to the access transistor without using an additional metal interconnect. Released in 1970, the 1 kilobit Intel 1103 DRAM chip revolutionized the computer industry with its cheap price, 1 cent per bit, and good performance. By 1972, the Core Killer, as it was called, was the world's single best-selling semiconductor chip, fuel for calculators, computers, and video game consoles. Unfortunately, Intel stumbled in bringing up the next generation of DRAM, 4K. This delay allowed other American firms like the startup MOSTech, which pioneered the 16-pin standard, and the ferocious giant Texas Instruments seize the initiative in the DRAM market. Fearing the intense competition, Andy Grove once said that at Texas Instruments, quote, they ate babies with nails over there, end quote, Intel edged away from the capacity rat race, though they stayed in the category. They turned their attention to 2 more profitable products. The first was a quirky little semiconductor memory invented by pioneer Dov Froman. Joining from Fairchild, Froman intended to work on metal nitride oxide technology, but was reassigned to troubleshoot an issue with the Intel 1101 failing at 85 degrees Celsius and 85% humidity. A few weeks later, he discovered that high humidity and metal contamination on the gate oxide let electrons leak from the source to the drain. He wrote it up and then moved on. But then, for reasons even he cannot fully explain, Froman realized that this issue can be used to make a new type of erasable read-only memory, suitably named Erasable Programmable Read-Only Memory, or EPROM. What is special about the EPROM is that you can shine UV light onto the chip through a little window to erase it. Pretty cool. They put it on the market as a highly priced prototype device, but it did not sell very well at the start. Later on, Dov Froman became the driving force for Intel's design and fab operations in Israel. The second major product category was logic, or microprocessors. Famously, these first came out of a collaboration with a Japanese company for a calculator chip. I shall spare you the widely told origin story. Intel proudly announced this new chip category in November 1971 with a splashy newspaper ad declaring a, quote, microprogrammable computer on a chip, end quote. A few years later, some hobbyists decided to put one of these Intel microprocessors, the Intel 8080, into a kit computer called the Altair 8800, the first microcomputer. Anyway, introducing the microprocessor also turned the EPROM into a success. The two products together let engineers program and reprogram their systems without needing to buy new ROMs. Sales of the high-margin EPROM took off. Andy Grove said, "DRAMs gave us fame, but EPROMs gave us riches." In 1979, Intel made $661 million in revenues and $78 million in profits. They had 5 factories in the US and Singapore and 14,300 employees around the world. Andy Grove was named company president, with Gordon Moore remaining CEO. They were on the top of the world. Made in Japan used to be a joke. Intel co-founder and legend Bob Noyce, then working for Fairchild Semiconductor, first traveled to Japan in 1960. He enjoyed the, quote, delicious raw fish, end quote, the nice clean streets, and presumably the female entertainment. And the Japanese businessmen there admired him as like a god, as they should. He co-invented the integrated circuit. Noyce also judged their semiconductor industry to be years behind America's. Their germanium products were mid-tier, their silicon far behind. So Noyce saw no issue with Fairchild licensing a few designs to the Japanese for additional capacity. Things then started to change. The Japanese started catching up. At first, the Americans poo-pooed it, saying that the Japanese were only so good because they stole American trade secrets and reverse-engineered American designs. But suddenly, there was no denying that the Japanese were doing something in the market. In 1974, every 4K generation DRAM sold was American-made. 5 years and 1 generation later, Japan had 35% of the 16K market. In 1978, Noyce traveled to Japan again to visit several customers and returned a changed man. He told Gordon Moore that Japanese semiconductor products had fewer defects than Intel's and that Intel needed to seriously focus on this. Normally a gentleman so kind and trusting they nicknamed him Dr. Nice, Noyce hardened against Japan. He saw in their rise a betrayal. And infamously, Noyce contributed to an article in the February 1978 issue of Fortune magazine titled "The Japanese Spies in Silicon Valley." Beyond its offensive header image, the article claimed that Japanese satellite offices in Silicon Valley were openly stealing secrets. Noyce was quoted in there as saying that the Japanese were, quote, out to slit our throats, end quote. They nearly threw him out of the country for that. Intel's customers were also pounding the drum on the company needing to get better at manufacturing. Gordon Moore recalled customer IBM repeatedly telling them that their yield sucked and needed to get better, and finally, IBM opened the kimono and shared hard data showing them as such. Electronics giant Hewlett-Packard was also confrontationally negative. 2 Intel employees, including one of Andy Grove's lieutenants, visited an unnamed VP in HP's printer division in Vancouver and was shocked to hear that VP say, "You know, I see this guy here all the time. I know he's trying to design Intel stuff into our products, but I go out of my way to design stuff out because I don't want service the way you do it, and I don't want quality problems the way you do things." Hewlett-Packard later went public with this dissatisfaction at a larger scale at a semiconductor industry presentation in March 1980, though some sources say this happened in 1979. HP's presentation had a slide showing that even the best American 16K DRAMs still had 6 times as many quality issues as the worst Japanese. It was remembered as a emperor has no clothes moment. A wave of murmur and disbelief rose up from the audience of executives. At first, Americans claimed that Japan's DRAMs were so cheap because they were just buying into or dumping into the market, and that Japan's DRAMs were so good because they were shipping only the good stuff. They were wrong. Japan's memory prices were so low because their yields were better. Much better. In 1980, Intel, its market position in microprocessors threatened by Motorola's famed 68,000 microprocessor, kicked off Operation Crush. Operation Crush was solely aimed at Motorola. The goal was to generate thousands of design wins for Intel chips and squeeze Motorola's market share down to 15%. It was a success, winning Intel some 2,500 design wins. One of those design wins was at IBM. So Intel had this rather strange microprocessor called the 8088. It was a variant of the 8086, which was a 16-bit microprocessor, but it communicated with the rest of the computer using the data bus of an 8-bit chip. This weird truck engine in a car's body arrangement, rushed out in just 18 months, helped keep the price down and let 8-bit enthusiasts get 16-bit performance without changing their whole setup. Earl Whetstone was a successful Intel sales engineer in the Florida area. One day, he gets a call to go down to an IBM facility in Boca Raton. They're working on a new product. Whetstone, not knowing what that product was, sells them on using the 8088. The weird thing is that IBM refused to say what the product was. Whetstone presumed it was a new printer or word processor, since that was what the IBM teams in Florida covered. But why the secrecy? Whetstone recalled, "When we went to provide technical support, they'd have our technical people on one side of a black curtain and theirs on the other side with their prototype product. We'd ask questions, they'd tell us what was happening, and we'd have to try to solve the problem literally in the dark. If we were lucky, they'd let us reach a hand through the curtain and grope around a bit to try to figure out what the problem was." That was 1980. It was not until 1981, when IBM started demanding that Intel provide second sourcing rights for this new 8088 chip, that Intel realized that this new product was more than just another printer. As I covered in a prior video, IBM insisted that AMD, who they were already familiar with, be the second sourcer. Grove didn't want that, but Noyce intervened. After all, Jerry Sanders, the former Fairchild salesman, was semiconductor family. A few months later, the two companies signed their famous cross-licensing agreement. By then, the IBM PC had entered the market in August 1981, an instant hit. In 1981, 13% of Intel's total sales came just from IBM, but Intel had no time to savor this victory. Dynamic RAM was Intel's baby, their first big product. They basically created the industry. But as early as 1982, the company knew that it was behind in this increasingly competitive category, perhaps hopelessly so. Intel's variant of 16K DRAM still had some unique engineering things that gave it some reason to exist in the market. Even so, in 1980, Intel had just about 3% market share. Worse yet, at the end of 1979, Fujitsu shocked the world when they unveiled a next-generation 64K DRAM made at volume. The Japanese, once looked down upon as mere copycats and spies, had pulled even with the Americans. Intel did some math and realized that their defect yields were not good enough to make a viable 64K DRAM of their own. So instead, they decided to try flanking Japan's advantages with innovation, something called chip-level redundancy. The latter refers to a nifty setup where extra memory cells built into the chip can be activated with a blown fuse whenever process-related defects are detected. But the fuses didn't blow right at first. causing Intel's 64K chips to hit the market even later than they already were, 2 whole years. Meanwhile, Japan ramped up their 64K memory production capacity from 9 million pieces in July 1981 to 66 million in August 1982, and they were already moving on to 256K. At the same time, the Japanese finally started to make progress on EPROMs, challenging Intel's 16K EPROM business worth $80 million in Japan. In response, Intel smoothly ramped up their next-generation 64K EPROM, temporarily vanquishing the challengers. 1981 had been a rough year, so difficult that Grove asked each employee to work an extra 2 hours a day for 6 months in order to avoid layoffs, the 125% solution. IBM was so alarmed that in 1982 they bought a 12% share of Intel to shore up their critical suppliers' finances. But fortunes reversed after mid-1982. Video game consoles, printers, and of course, the personal computer. Sales of these devices boomed, fueling microprocessor sales. We were so back. It was that year that Intel crossed over, selling more logic than memory for the first time. And it was about here, 1982, that a few inside Intel, like their general manager of memory, Scott Gibson, started advocating for the company to leave the business. He predicted that the margins of DRAM were going away, and at the very least they should focus on niche memories. Niche like the EPROM, of which Intel still maintained majority share. The Japanese struggled to make a good EPROM chip at scale. The physics of its floating gate were weird, and the process was as much art as science. But just as many within Intel argued against leaving the DRAM product line. DRAMs made Intel a one-stop shop. Some customers liked that, and ending it would make them angry. And DRAMs were seen as a, quote, process driver, end quote, as in, expertise learned from making DRAMs can theoretically be applied to making microprocessors too. EPROMs can't do that. They're too weird. And of course, DRAM was Intel's baby, their first child, the product that took them from a two-man startup to a Fortune 500 giant. How can you leave that behind? 1982 and 1983 had been a brief respite that let Intel try to shore up its manufacturing. And thanks to increased investment in testing equipment, quality control techniques, manufacturing automation, and human operator training, the defect rate fell from 8.5 per million in 1980 to just 1 in 1984. Yields on microprocessors doubled to 50%. But amidst this improvement, gathering storm clouds in 1984. Booming memory sales in the first half of the year lured the industry in both the US and Japan to rapidly expand capacity. Then everyone got hit in the face when, in the fall of 1984, the economy, the industry, and the silicon cycle suddenly turned. DRAM prices crashed, the American DRAM makers exited the market, blah blah blah. I covered this multiple times. But another thing that happened was that EPROM prices crashed too. The Japanese, burdened with capacity, cut prices on their EPROMs by 70 to 90%, hitting sales of Intel's critical money-making chips. The company lost money for 16 consecutive months in 1985 and 1986. In 1985, revenues fell 16% and profits vanished. Intel and the rest of the American industry blamed Japan for this EPROM glut. In mid-1985, Hitachi, maker of the Hitachi Magic Wand, sent a memo to its EPROM distributors. It told them to slash prices and get market share at any cost. Quote 10% below their price. If they requote, go 10% again. Don't quit until you win. And, much like the Hitachi Magic Wand, this memo was eventually used for purposes its maker did not originally intend. In October 1985, AMD, Intel, and National Semiconductor together filed a trade petition against the Japanese EPROM makers, accusing them of dumping. It was one of the major contributors to the eventual 1986 US-Japan Semiconductor Trade Agreement, which put a floor on EPROM prices and helped Intel recover. By late 1984, Intel's share in the 256K DRAM market had fallen to just 4%, and they were totally out of the 64K market. Now Intel's people ramped up again for the next generation 1 meg DRAM. Based on the research that the DRAM group had prepped for the meg, it looked to be a beautiful product. But again, inside the company, there were feelings. Intel had chased this dream for 2, 3, maybe even 5 years, but it was not coming. The meeting in which Intel decided to get out of DRAMs is famous. They teach it all the time in business school. In mid-1985, Andy Grove goes to meet Gordon Moore. I was in my office with Gordon Moore, and we were discussing our quandary. Our mood was downbeat. I looked out the window at the Ferris wheel at the Great America Amusement Park revolving in the distance. Then I turned back to Gordon and I asked, if we got kicked out and the board brought in a new CEO, what do you think he would do? Gordon answered without hesitation, he would get us out of memories. I stared at him, numb, then said, why shouldn't you and I walk out the door, then come back and do it ourselves? It's a dramatic story, but I think it somewhat overstates the reality. Let me quote Intel's Craig Barrett, who will figure into this story later. The other side of the story was, we were effectively out of DRAMs when they got up and walked out of the room. Laughter. See, whether that was a symbolic gesture as opposed to a decisive moment in history is up for debate to some degree. Even after the meeting, it took another year to implement the decision. Grove moved the old general manager and told his replacement to make the cuts, but then that new general manager kept holding on to the 1 megabit memory R&D program. So all in all, Intel left DRAM kicking and screaming. Just like as they did with AMD for the US market, Intel second-sourced some of their microprocessors to NEC for the Japan market via a patent license. In 1979, NEC started producing Intel's 8086 and 8088 chips. But soon after that, they began making a new line of NEC chips that were, quote, Intel compatible, end quote, the V20 and V30. To make the V20 and V30, NEC reverse engineered the hardware in the same way Compaq reverse engineered the IBM PC BIOS, a clean room approach in which one room makes specifications and another room makes the hardware without ever looking at the original Intel chip. And this was allowed because the circuits were patented and cross-licensed. However, by then Intel had introduced what is called microcode to their CPUs. This refers to code that is embedded directly into the processor hardware. It's basically very low-level firmware for the CPU. Feeling it necessary for full compatibility, NEC copied the microcode and Intel saw that as a violation. So they went to court, and the court agreed with Intel's assertion that microcode can be copyrighted. For more information, I recommend the Chip Letters write-up on this. Intel realized that this, along with the photomask design protections granted by the Semiconductor Chip Protection Act of 1984, can be an effective legal cudgel against unauthorized copying of their chips, like those by fabless startups like Cyrix. At the same time, Intel was preparing their next big microprocessor, the 386. Their first 32-bit chip, and quite powerful, armed with twice as many transistors as the older 286, the 386 was a fine chip. They offered it to IBM, the biggest and most important customer by far, for use in their next PC, basically begged them to take it. And famously, IBM said no, in part because they worried that the 386 was so powerful that it would cannibalize their mini-computer business, but also because they wanted to retake control of the PC ecosystem with what would eventually be called the Personal System 2, or PS2. The PS2 represented a closing down of the open PC ecosystem. For instance, IBM was working with Microsoft for its own OS, so at least for a little longer, they wanted to use the older 286 chip since that was what they owned the manufacturing rights for. As one Intel employee said, they were totally focused on doing this internally. Andy Grove saw these two events, the microcode win and IBM going off on its own, and recognized an opportunity to have Intel own the x86 ecosystem for itself. He pushed for Intel to sole source this 386 chip, as in being its exclusive provider. He wanted this for older products before, but Noyce and the customers had overruled him. This was a major risk. It antagonized AMD's second sourcing business, eventually leading to a flurry of lawsuits between companies that had once been like brothers. It later antagonized IBM because Intel worked with Compaq to produce the Desk Pro 386, challenging their power. And it put a lot of pressure on Intel to ramp up its manufacturing enough to supply a whole market. Can they do it? Thusly, the cornerstone of this whole strategy sits on top of manufacturing. Intel can't get the x86 monopoly it wanted if they can't make enough good chips to meet demand. That's one of the reasons why second sources exist, having that additional quality and capacity in case something goes wrong. For this, Intel had Craig Barrett, their new head of manufacturing. Big and burly, he had been a track star back in the day. Barrett held a materials science PhD from Stanford and was a tenured professor there. Then in 1974, he took an unexpected one-year sabbatical to join Intel as a technology development manager at the Reliability Engineering Group. Their job was to make the products reliable. He soon thereafter stayed. Barrett joined as a technologist, but soon narrowed in on operations. In January 1985, he was made head of all the fabs. Grove and Moore asked him to cut all manufacturing costs in half by 1985, and then half again in 1986. Barrett thus led a painful downsizing, closing older and unproductive factories, including a bevy of plants in California, Oregon, Puerto Rico, and the Caribbean, and cutting nearly 30% of company employees. Then Barrett got to work on fixing Intel's manufacturing. They studied Japanese techniques. They adopted Japanese standards of cleanliness. They pushed their suppliers for pure materials and chemicals. And most of all, they copied exactly. Most Silicon Valley companies in the 1970s worked like larger corporates. New processes and techniques were first developed in the R&D laboratory and then moved to production lines. The problem, however, was that time was wasted trying to figure out what the lab actually did and adapt that to the production machines. So at Intel, they made the R&D teams experiment on new techniques right on the production lines. This way, the R&D engineers worked right alongside the production engineers and used their equipment. But this created new problems. Managers in various fabs liked to tweak things on their own lines. That made transferring knowledge hard because there was no consistency between each of the R&D lines. Removing these variations was key. An example, one time Texas Instruments was transferring a line for some memory product from Miho, Japan to Dallas, Texas. The Dallas line was supposed to be exactly the same as the Japan one, but then the US line manager decided to be a cowboy and quote-unquote tweak the process, crashing the line and delaying the transfer by months. They had to call the original Japanese manager to Dallas to fix it. So Barrett retooled the whole organization around a concept he called copy exactly. Intel's old DRAM fab in Oregon got turned into an R&D fab where staff experiment to produce a line with high yields at high volumes. Once that is achieved, manufacturing teams step in and copy the process as exactly as possible across all of the fab sites. When moving to a new site, the whole plant is replicated with the same supplies, options, and physical dimensions right down to the size of the valves and pipes. Barrett got the idea from McDonald's. He started by wondering why McDonald's fries tasted the same no matter where they were. He decided to make Intel the McDonald's of semiconductors. Despite resistance from engineers, who wants to be hired to just do exactly what someone else says, copy exactly worked right off the bat. Intel's yields soared, and the company ramped up microprocessor fabs around the world, feeding the PC revolution for years to come. What we tend to most remember about Intel's return to the shore was its turn away from the DRAM market. The reality, as it always tends to be, was a bit more nuanced. Yes, the turn away from DRAM mattered, but less than you think. Intel effectively lost DRAM back in the 4K generation. The company's market share was closer to 0 than 10. They were already out. I argue that it was more a combination of three different things. First, the trade petition against the dumping of EPROMs, which halted the Japanese onslaught against their actual cash cow. Second, the microcode victory against NEC, and the momentous single-sourcing decision of the 386, which effectively locked in an x86 monopoly, the new cash cow. And third, the cleaning up of Intel's long problematic manufacturing processes personified with copy exactly. These three things saved Intel, it made them a centi-billion-dollar company, and it has also brought them to where they are today. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the newsletter, and I'll see you guys next time.